All right, here we go. 2, 3. Graphs that help and graphs that don't help. Playing a little samba in the background, a little jazz. Hopefully it makes the stats go down easier. We'll bring down Gilberto here just a little bit. All right. So there's many types of graphs. And the idea is that you make and read graphs carefully. All right? Big picture. There are many types, so choose carefully. It's kind of like a box of chocolates. But whatever you do, don't lie. All right, we got dot plots. I don't know that you need to write any of this stuff down. I think you know that dot plots are numerical or categorical, but they use dots instead of bars. So again, here we've got pulse rates of males. I don't know what age groups, but you can see the dots there above the different classes. Looks like our class width is 2, because we got 5 classes in each group of 10. All right. Stem plots. This, you might write something down here. Again, stem plots could go numerical or categorical, though I would say it's probably going to be mainly, no, this is just numerical. I don't know what I was thinking. No categorical things here. And these are digits instead of, can't write and talk at the same time. Digits instead of dots. All right. And we use a horizontal kind of bars, not vertical. And the leaf is 1 digit. Typically they call them stem and leaf graphs. So here is a picture of a leaf graph. Stem plot, sorry. And we have the stems out here, and then the leaves are in here. These are the leaves. That shows us kind of the shape, right? We can see the normal bell curve. So it's a little bit like if you mixed a histogram with the digits instead of the numbers. It's kind of what you would get, right? And it shows you the stems are in tens. So this is a 40, 50, 60, right? So our largest 2 data items are 102 and 104. And we see the 2 and the 4 there. And that's why we have to make sure that the leaves on the right side are just 1 digit, whereas the stem is whatever else is not that digit. Okay? We see a lot of even numbers there for those pulse rates again. We talked about that in class a little bit. Time series graph. This certainly is one you've done before. The x-axis represents time, and the y-axis is typically some sort of quantity. So you have 2 paired data. And I think one thing that you want to remember here, especially on the time axis, don't start with 0, right? You're going to start with some other value. In this graph here, we see our time graph is starting at 1985. In our y, this can be devious. We'll talk about that in a moment. We shouldn't really start at 100 unless we have a really good reason. We don't want to distort things, but sometimes we have to start at a number other than 0 on the y. All right. Notice there's no natural 0 in that problem too. We were talking a little about interval and ratio orders, and that's a typical case of an interval data time. Bar graph. Bar graphs always use categorical. And they're simplistic, but they compare quantities very well. Yeah? Nominal or ordinal data could be used. So here we have nominal data, meaning these are names, right? There's no order to these. We have the bars, and these are written in, notice, descending order. So therefore, this is a special bar graph. It's called the Pareto bar graph. And that's the only distinguishing factor between Pareto graphs and normal run-of-the-mill bar graphs. Okay. Pie charts. Leave the pie charts for the newspaper for many reasons. Number one, you must have 100%. Now, technically, are there other types of boats other than the ones that are listed? Like, are you going to suggest that rowboats or canoes are not stolen? Secondly, you've got to be able to compare, and it's hard to visually see some of these comparative values when we see them as pie charts, wedges. Again, it's categorical data, but the fault is comparisons. So they're not taken very seriously in the world of statistics. This one is another one that you might want to jot down. It's a frequency polygon. It's like a bar chart. Okay. The only difference is that instead of we've got bars, and in the middle of those bars we take a midpoint. All right, and that midpoint becomes the mid. What do we call it? The class mid value. Yeah, and that becomes the point that you make a dot, and then you just join it up with a. You can see also area-wise, this piece compensates for that piece, this piece compensates for that, right? So we're not like fudging on data per se. We're just expressing it differently as a progression. And they connect to create a polygon. And we use those class mid values. All right, graphs that deceive. Hopefully by now you realize that these types of graphs may be used for little kids, but as adults who make rational decisions, this should not be done. Easiest way to see that, just make a little line of all the threes, right? And tigers, wolves, and bears, okay, but zebras, you can't do that. Yeah, there's a distortion going on. And that distortion only gets worse the more they become. So it's cute to use a picture, but two-dimensional is not one-dimensional, right? We don't want to use areas to compare heights. And so here we have a height, and we're using the little area of the animal to draw that height out, and those heights are not equivalent. Okay? The other distortion that you'll see, I wish I could get my fingers on it. I saw one at the beginning of the year in our staff meeting, very similar to this one. And I had to ask myself kind of halfway through the meeting, like, were they being devious in their presentation? But 10% is where that scale starts. This one starts at 0. That's the big difference between these two data sets. And notice it's not lying to us, right? Our values here correspond to the correct values. But when our eye sees this, we go, oh yeah, Oxycontin is way better, right? When it's only twice as good. All right. So vertical axis distortion is what we call that. Very common practice. And we've got to watch out when the lowest value on the y-axis is changed. Final few conclusions here about looking at this data. Number one, don't use a graph when your data set is small, right? Make a little histogram, that type of thing. Don't table it up. Number two, don't distort, right? Oh, sorry, not distort. That was the last one. Don't distract from the data. Pie charts tend to distract. You want to pick a graph that helps inform your argument, right? If you want to make an argument about comparative values which are going down, do that. If you've got time, make sure that you use a XY axis so that you can see that. All right? Okay, moving down the road, let's go to 2.4. This is the trickier of the two sections. Scatter plots, correlations, and regressions. We are hunting for relationships. And we want to, first of all, talk about correlation. So a correlation is an association. I didn't spell that right. Association between two variables. That association can be positive, negative, or constant. All right? I forgot to do the big idea. This whole unit is about paired data, and the two things are linear combination, or linear coefficients, or regressions, and correlation coefficient. First of all, linear correlations. They're plotted pairs which resemble a line. I'll show you some pictures of that in just a moment. Scatter plots are quantitative data, not categorical data. So these are numerical on both axes. And one thing that we want to be really, really careful is that correlation does not mean causation. All right? We've talked a little bit about that in class. Ice cream and swimming. There's a correlation between them, not a causation. So here's some examples of a correlation. Here we have a positive and linear, but it's weak. Notice, does it resemble a line? Yeah, but it resembles a really thick line. The closer these dots are together to just one line, say that one, that would then tell us. Some people mistakenly think we have to go through 0, 0 to be also, and that's false. Right? Okay. Here, clearly there is no correlation. Usually this means, number one, two things. Either there is no correlation between these, or we have some other confounding variable in here that we're not paying attention to. So we might need to disaggregate by maybe race, gender, maybe hypertension, or maybe there is no relationship at all between them. Okay? And then finally we looked on this on the pennies. These are called clusters. Okay, we got a cluster here and a cluster here. The one on the right, there's nothing here. Okay, does not look like there's anything that is giving me any type of trend. There's no linear correlation. On the other one, there is, there appears to be a linear. The only thing weird about this graph is I would have switched my axes around. I would have put the weight on the vertical and the year on the horizontal. It looks like a fairly constant value. We can kind of see what that weight was. Okay? All right. Finally, we close up this chapter, this unit, and this chapter with the coefficient of correlation. It's called R, and it determines the fit of the data. And this is an important fact to know, right? R is the correlation coefficient. We use calculators or spreadsheets to find that R value. First of all, we need to know that the R value occurs between -1 and 1. And if it is a perfect fit, meaning the dots form a perfect line, you will either get 1 or -1 depending on the slope. The slope doesn't need to be 1, right? It just needs to fit the line perfectly in a positive sense or fit the line perfectly in a negative sense. If it is somewhere in between, and that's usually the case, then we have either some correlation that's positive or negative, and that's the tricky part. All right. So here, using the stat disk, I think we could also do this on our stat crunch. I'm not entirely sure. But we can see that there is a rough linear relationship, maybe like this. I don't know if that's exactly what it would be, somewhere in that region. Okay. Now we see that the R value up here is 0.91 or 0.591. And that tells us it's slightly positive. Okay, and that there is some slight relationship. Now, a couple things should tell us this is not a good correlation. Okay, number one, we see this big gap here between what would be the line and the dots. And then we're going to talk about this p-value here. And this p-value and this number here kind of give us a little clue. You recall in algebra class we actually wrote the equation out there. There's the y-intercept and there's the slope. Okay? One thing we'll see at the very end, that n is 5, you're not going to get good results from n equals 5. All right, first things. How do we know if I can lean heavily on this R value? So here's n, the number of pairs, and as the number of pairs increases, our critical value goes down for R. Now what does that mean, the critical value of R? That means for us to be like dependent on R, to trust the R value is good, I need to have R values that are bigger than 9.5 if I've only got a 4. We had 5, so therefore if our R value was less than 0.878, I think this should say between positive or negative. Okay. Likewise, you can see as it goes down, the more n values you get, the more you can trust, because anything above this, right, on the outsides of that value is trustworthy, so to speak. All right. So here we can see a clear graph of what's going on. Again, we see the R values down here, and we see our R value of 0.591 right here. And because n equals 5, we have to be here. We have to be within this little range to be trustworthy correlation. So clearly, there is no correlation. This is outside of the critical values. All right, so what is the p-value? This is the probability, yeah, that the R value is good. Did it happen by chance? So in our problem, we had an R value of 0.29, 29%. That the correlation is due to chance. All right. Now you might think that's actually pretty good because that's like a 60, 71%, but it's actually bad. You need to have this down, less than 5% to be able to say something is trustworthy. So here they did the graph again. This time they went back and they got a lot more values. In fact, I think n is 50, or no, maybe it's just 40. There's 40 dots here. And our correlation coefficient has gotten bigger, closer to 1. More importantly, our p-value has gone down to nearly 0. It's not exactly 0, it never is 0, but it's close to 0. And what we then can see is that as long as my R value is above 0.312 or less than negative 0.312, then we can say there's a correlation. Okay? So there is something between shoe print and height. So there's the final thoughts there. As n increases, we get better results, and we can be more confident in there being a correlation.